Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of supermarket sales. Each record on the dataset is an invoice, and at the end we have a rating given by a customer about how their overall shopping experience was on a scale of 1 to 10. And we're going to train regression models to try to predict the overall satisfaction of the customer based on these features. We're going to be using pipeline, so I'm importing, we're importing NumPy and pandas for working with the data. And then from sklearn, these are all for pre-processing. We're going to get the train test split function, pipeline, column transformer, and then ordinal encoder, one-hot encoder, and standard scalar. And we will also construct our own transformers or encoders to use for the date features, date and time features. So we're going to train on a bunch of different models today, a bunch of different regression models. So I'm importing all of those. We have 3 different linear regression models with different types of regularization. K-nearest neighbors, regressor, a neural network, 2 support vector machines, one with a linear kernel, one with a non-linear kernel, a decision tree regressor, and then we have a bunch of ensemble models as well, which is random forest, gradient boosting, XGBoost, LightGBM, and CatBoost. So let's go ahead and import all of that and load in the data using pandas.readcsv. We can grab the file path to the CSV file up here. Let me just zoom up on this a little. And we can look at the data. So we have 17 columns. The invoice ID is not going to be of use to us. So why don't we get a little more information to see if we have any missing values. We can see from this there are no missing values in any of the columns. We also have 9 object columns that we're going to have to encode. So we can start, I'll call this initial pre-processing, because we're not going to do the pre-processing directly on the data. We're going to fit pre-processing objects that will actually perform it when we fit the model. So what this is going to do, this is going to set up the inputs. This is basically is feature selection. We're saying which of the features are we going to use for our model. And this is sort of up to us. What kind of model are we going for? So we'll create a function called preprocess inputs, and that's going to take in a data frame. And right now it's going to make a copy of the data frame and return, I want it to return the target and the feature data separately. So split df into x and y, where y is going to be our rating column, because that's what we're trying to predict, and x is all the rest of the data. Sorry, this should be df sub rating. And then we're dropping rating and storing that in x. And then we'll return x and y. No, not an and, comma. Okay, we'll get them back over here. So we can sort of decide which of these columns do we want. So what I mean by that is, obviously we want as many as we can that are going to be useful for making predictions, but we have to consider the task. For example, if I was going to use this model to make predictions for any supermarket in any place, then I would want to remove the branch and city columns. A reason for that is because branch and city are specific to supermarkets that already exist in the training set. What I mean is, if we have a new supermarket that's not in the training set, then these columns don't really tell us anything, because these columns, the presence of these columns helps the model identify what kind of shoppers shop at certain supermarkets A, B, and C. It's using this column to know what are the habits of the shoppers at those particular supermarkets. So if we now introduce a new supermarket D, the model wouldn't know what to do with it. At least concerning this column would not be of much use to it. Same with city. If we introduced a new city that the model has not seen, then it wouldn't really be able to use this column. However, probably the more typical example, more useful maybe, is, let's say this supermarket company has these 3 supermarkets, and they want to know at their current supermarkets what is the satisfaction rating of a given customer. Then this column becomes useful because we want to know which supermarket the shopper is at. Same with city, and it's pretty much same with all the rest here. These are all useful in that sense. One thing that's a bit interesting, date. The year at least, it might not be so useful. Because you think about it, if this were used in real time, the year will always be the most current year, or in other words, a year that the model is not very experienced with, because it's present. However, month is very useful because time of year is important. Time is useful because time of day is important. But the year itself might not be so useful. We'll keep it on anyway. It's not essential that we drop it, but I'm not sure that it will contribute much information if we were to try to make predictions on new unseen data from current day. So if we took the test set out, it might use the year in the test set to make accurate predictions because that's on past data. But if we were to try to evaluate the model on future data, then the year stops being as useful. Okay, so so that was sort of like philosophical, but we're going to keep all these columns. We're going to try to make this model work for just these 3 supermarkets. So keeping this on works well. We don't need this column. The invoice is unique for every record, and it's not going to contribute any information to our predictions. So let's actually go and drop it in our preprocess inputs function. Drop ID column, and that will be df equals df.drop invoice ID from axis 1. Alright, you can see invoice ID is gone. And now let's do the train test split function. Let's do the train test split now. So train test split. So let's send 70% of the data to the train set, and we'll have the other 30% in the test set. So that will give us 4 new sets of the data, which will be xtrain, xtest, ytrain, and ytest. And we're going to use the train test split function from sklearn for this. We'll pass in our x and our y, specify the train size, how much of the data do we want to contribute to the train set, so 70% works. And shuffle equals true is on by default, and basically that means we'll shuffle the data before we make the split, and because we're shuffling, we'll include a random state to ensure the shuffle is always done in the same way. Okay, so let's grab this, and let's just look at xtrain. Alright, so xtrain is now only 700 of the original 1,000 rows, so 70%. And ytrain should be the same 70%, but the labels associated with them. Okay, so let's now construct our pipeline. So a pipeline is a way to feed in human readable inputs like these, turn them into machine readable inputs, and then make predictions on them all in one pass. So what the nice thing about pipeline is that you don't have to pre-process your data on a case-by-case basis. You just pass in the data in its original form, and the pre-processing is already done for you in the model. So let's start by categorizing our features. This is very important if we're going to create different types of transformers for each type of feature. So let's figure out what kind of features we have. When we are constructing the pipeline, we only want to do it with the train set in mind. We're only constructing it around the train set. We're going to fit all of the pre-processing, like the scaler and the encoders, all to the train set only, because we want to pretend we don't have access to the test set. Test set is supposed to be as close to unseen data as possible. So we don't want the model to consider the test set when we're doing this pre-processing. Alright, so we have some numeric columns here. Numeric columns we're really not going to encode at all. We'll just scale them at the end. So unit price, quantity, tax, total, COGS, and then these last 2 columns are all numeric. So we're going to leave those alone. We can get the other features with xtrain.select dtypes object, and that will give us just the object columns, so none of the numerics. And now we can get a little more information about this by taking this and we want to find out what is the number of unique values in each of these columns. So we can create a dictionary that will map the column name to the number or the length of unique values in the column. That will be xtrain subcolumn dot unique, and we're taking the length of that, and we're doing this for every column in these object columns. So select dtypes subobject dot columns. Oh, I forgot the in. Alright, so we can see how many we have in each one. First thing I noticed is that we have some with 2. When you have 2 unique values in a column, those are binary columns, and they're the easiest to encode. You just send one of their values to 0 and the other one to 1. So let's say binary columns, binary features we'll say. This will be customer type and gender. So just make it like this, so it's a list. Then we have some date features. So there's one date feature, that's the date column. Date feature I'm handling separately because it's not, even though it's categorical, it has numeric information in it. So all we have to do with the date feature is go in and extract each bit of information. We're going to pull out the year, pull out the month, pull out the day. For the time is very similar. We're going to pull out the hour, pull out the minute. So date feature is just date, and then I'll make time features as well. And that will just be time. Then last we have nominal features. Well, actually we should check if we have ordinal or nominal. Of the remaining columns, if we have more than 2 values, and we're not dealing with date time information, then they're all candidates for either ordinal encoding or nominal encoding. So ordinal encoding is where you send each of their values to an integer in a continuous range. But that's only good when you know the spacing between the values. Even if there's an order between the values, if you don't know how to space them, you should just treat it as a nominal column. And a nominal column is also called a one-hot column. We can use pandas.getDummies to show. Nominal column, let's take branch. If we take xtrain subbranch and call pandas.getDummies on it, each branch gets its own column, and there will be a 1 representing the original branch of that example. All the others will be 0. So this will give each unique value its own column, and won't worry about the ordering between them. Now, I don't think there's any ordinals here. The branch, there's no ordering between these values. The city, there's no ordering between these values. These two are binary as we saw. The product line, no ordering between these values. Date and time, we saw already. Payment, there's no ordering between these values either. So these are all nominal. The remaining columns are nominal. So that will be branch and city. Then we have product line and payment. Alright, let's just clean this up. Okay, we'll just indent them back, push them forward. And there we go. Okay, so we have all of our columns defined. Next thing we'll do is create some new transformers to deal with the date and time features. So we're dealing with this first because sklearn already comes pre-equipped with ordinal encoders and one-hot encoders, and that's what we're going to use for the binary and nominal features. We'll use an ordinal encoder for binary features without any care about which value gets sent to 0 and which value gets sent to 1. If you want to choose the value that gets sent to 1, it really doesn't matter in terms of the model's performance, but if you do want to for some reason, you can specify that in the categories argument for the ordinal encoder. For the nominal features, we'll use a one-hot encoder, which just does this pandas.getDummies thing behind the scenes. And then for date and time, there's not really a great way that comes with sklearn, so I figure we'll just create our own. So if we're creating custom transformers, let's say for date and time features, all a transformer has to have, you have to implement a fit and transform function. So let's make a date encoder. That will be our date transformer. We need a fit function that takes in x and y, and we're also going to need a transform function that just takes in x. So for fit, fit will be used to store any information about the data before the transformation is applied. And in the case of this date transformer, it's really just an algorithm. It doesn't need any information about the column in order to pull out information. Maybe if you had scrambled formats for dates, maybe then it could go in and memorize all the proper formats. I don't know. If you wanted, you probably could find some way to make use of the fit function, but we're not, so we're just going to return self. So this function does nothing. For transform, this is the part that actually does the work. Keep in mind that x coming in is actually a data frame. It's not a series, it's a full data frame, possibly with multiple columns. So we could pass in multiple columns here into our date features that would be contained in x. So x is a data frame full of only date columns. Consider it that way. So for every column in x.columns, because we know they're all date columns, that's what we're passing in here, we're going to apply these transformations. So let's take a look at this. Let's look at the date column. I'll do that for xtrain. How do we want to pull out the month? How do we want to pull out the day? How do we want to pull out the year? One way to do this might be to use a lambda function to take out just maybe the first element of every example. That would give us back the month. However, as you can see, there's a problem. If we have a 2-digit month, it's not going to give it to us. So the next thing to do might be, well, we could use regular expressions to grab all the text before the first slash. And that could work. However, there's a nicer way to do this. It's using the pandas.toDateTime function. And we can convert the column into a datetime column like this. You can see the object type has changed to datetime64. And what's nice about datetime objects is now, instead of using some regular expressions, we can actually just say x.year and get the year back, or x.month and get the month back as an integer, note, and x.day. And that will work. Similarly, for the time, if we do x.hour, we'll get back the hour, and x.minute, we'll get back the minute. So this is how we're going to do it. In here, for a given date column, we're going to convert that column into a datetime column. So x subcolumn equals pandas.toDateTime of x subcolumn. Now once it's converted to a datetime, we're going to apply a function like this. We're going to take x subcolumn dot apply lambda x, and we'll just take the year out. Now what do we want to do with these years? We're going to store it into a new column called column plus underscore year, like that. So let's say our column name is date, then this will come in, convert date into a datetime column, and then create a new column called date year, consisting of just the years from the date column. We'll do the same thing for month and day. So these will become month, these will become day, and we'll just put the underscores here. And then, when we're done, we've taken all the information out of the column, so we don't need that column anymore. So x equals x.drop column from axis 1. And we're going to do this for every column we pass in. Now, I'll note for this particular case, we only have one, but we are writing this so that it could work for as many as we pass in. And then we'll return x when that's done. Alright, let's do the same thing for time. Why don't we test it out first? Let's create a new date encoder object, and we'll use the transform function of it to transform xtrain just the time column. You'll note I used the double brackets here to have it return a data frame instead of a series. And you can see it pulled out each bit of information, stored it in its separate column, and these are already encoded as integers. So it works well. Let's do the same thing for time. So this is going to be our time encoder. Fit function stays the same. We don't want to do anything with that. For transform, only thing that's different is instead of pulling out year, month, and day, we're pulling out hour and minute. So let's change these to hour and these to minute, and then add those underscores. Alright, and that should be it. They're very similar. Now what we can do is set up different transformers for different types of features. So I'll say this. I'll say construct transformer pipelines for each feature type. So we're going to make sort of like sub-pipelines, mini pipelines to put into our main pipeline at the end. Each one will be called a different kind of transformer. So we'll have our binary transformer, that will be a pipeline. We'll have our date transformer, that will be a pipeline. A time transformer, which will also be a pipeline. And finally a nominal transformer, that's our one-hot transformer, that will be a pipeline. Alright, so what goes in these pipelines? Each of these pipelines takes in an argument called steps, which is what transformers are we passing the data through. And each of these is only going to have one step, which is going to be whichever transformer is being used for a different type of information. So for binary, these actually should be tuples with a name and then the actual transformer object. So for binary, we're going to create a new ordinal encoder to use. And here's where you would specify your categories if you want to choose. Categories, by default, it's auto, but you can also specify it as a list of with the ordering that you like. Let's say you wanted yes to be first, no to be second, something like that. I'm not going to use it. It's on auto by default. And then here we give it a name. It shouldn't just be ordinal. And then for date, we're going to use our date encoder that we just created, and that will be date. This will be our time encoder. New object, and then that will be time. And finally, our one-hot encoder. This comes from sklearn again, which will do the dummies for us. We'll call that one-hot. All right. Now we're going to combine them all together and tell the pipeline which columns to target with each transformer. So combine transformers, and for this we're going to use the column transformer class from sklearn. So column transformer takes in a number of transformers. Now these also are tuples with a name and a transformer, except we've already created the transformers, so we don't have to plug this whole thing in. We can just type binary transformer, and then we also specify which columns we want to target with the transformer. So binary features is what we're after, which is that list of our binary features up here. So we'll give this a name, binary, and we're going to apply the binary transformer to the binary features. Then we'll do the same thing for the remaining types. So then we have our date. This will be our date transformer that we created right here. And we're applying this to date features. Then we have time. That's our time transformer. And we apply that to time features. Finally, we have the nominal, which is our nominal transformer. And we're applying that to nominal features. Alright, and let's call this preprocessor. So now we're pretty much done. We can start training. We've set it up, and this preprocessor will take care of all of the preprocessing for us. We've specified how to preprocess and which to preprocess for each type of feature. So we're going to define our models. like I said, we're using a whole bunch of different models today. For the sake of time, I'll just copy this in. This is going to be a dictionary that maps the name of the model to the instance of the model. And what's nice about this is we can iterate through each model and fit each one using the same preprocessor and the same scaler. So we actually have to make a scaler. A scaler will give each column the same range of values. We're going to use a standard scaler, which will shift and scale each column so that they all have mean 0 and variance 1. Then, for each model, what I'll do is get the name and the model. For name and model in models.items. So .items allows us to iterate through a dictionary the key value pairs 2 at a time, like this, as a tuple. And then construct the final pipeline. So we're going to create a new pipeline for each model using the same preprocessor and scaler. So it doesn't matter if we refit the preprocessor and the scaler, because the data is always the same in this case. But we will want to fit a different model each time. So we're going to create our pipeline, and this is going to be a new pipeline object with the steps given by, we're going to have 3 steps. We'll have the preprocessor first, and for this we just pass in our preprocessor that we created. That's this thing here. Then we have the scaler, and that's going to be a standard scaler. Oh, sorry, that's going to be this scalar object we created. We don't want to create a new object here, because then we would not have the fit available to us when we evaluate the model later. Then we have our regressor, and this is the actual model itself, machine learning model. And that's going to be model, which is whatever we're passing through this list. And once we've created the pipeline, we're going to fit it. So that's pipeline.fit xtrain ytrain, and we'll print out a little confirmation message that says that the model was trained. If I have an error, float argument must be a string or number, not timestamp. Oh, interesting. So that since it's talking about timestamps, this is probably something to do with our date transformer. Let's look up here and make sure everything's good on that. Our date encoder here. Give me 1 sec, I'll figure it out. I figured it out. We forgot to drop the original timestamp column from our time encoder. So that's the same as up here. Let's put that in. Okay. Oh, there we go. Okay, let's try this one more time. Another error. Wait. Oh, right. So we redefined the class, but we forgot to recreate the objects. So let's go. Just delete these. Run this, run this, run this, run this, run this, and check it out. There we go. They're all training now. And they finished. Let's take a look at the results. So for the results, we actually want to reconstruct the pipelines. Now the preprocessor and scalars have been fit, but our pipeline object, if we look at it, it's now just using the last regressor we used, because the same pipeline was, pipeline was a local variable within this for loop. So we can't just use that pipeline because we didn't save one for each model. If you want to, you can, but it's not really necessary since we can just refit. Since the preprocessor and scalar have already been fit. Since we declared them outside of the scope of the for loop, they still have the fits from the last regressor, but they will be fit the same way regardless of what regressor we use. So we can just use them again here. So we're saying for each name and model in models.items, the same we did before, we recreate the pipeline, which will be, it will have the preprocessor, which has already been fit. Here we're not fitting it again, we're just going to evaluate. So preprocessor. And then our scalar, which has already been fit. And our regressor, which has also already been fit here. This is going to be model. And so we're drawing from the dictionary of now fit models, or these are all fit now, so we can just grab it like this, and then we'll print out the R-squared score for each model. So R-squared score is a way of evaluating the performance of a regression model. It pretty much measures how dispersed the data is around your fit. So we'll say the name of the model plus R-squared score, and we'll display the R-squared score to 5 decimal places and format this with pipeline.score of xtest, ytest. So we'll now send the test data through the preprocessing, the scaling, and the regressor, and then get the score. Alright, and you can see how they compare. They're pretty much all the same. The best R-squared score you can get is a 1, which none of these are anywhere near. But the worst R-squared score you can get is unlimited. You can get as negative as you want, as it wants. So I would say the best one here is the lasso regularization, the L1 regularization. This is just simple linear regression, but it does have the highest R-squared score. None of them are doing particularly well. So maybe there's not really sufficient. It's hard to say if this is good or not, right? Without a baseline to compare it to, you can't really say. But we do get to see how different models compare to each other, which is useful. And that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.